Okay, I don't know if you watched or didn't watch that introduction, and I didn't want a 9 minute introduction for us getting right into the math, so I decided to make that a separate commentary, okay, on my philosophy and my understanding of mathematics, um, and how I believe that anybody, if they put themselves to it, can amaze themselves as to how far they can come along with mathematics. So last video we were dabbling into the realm of exponents and bases. So we'll continue in that line. We've got what we call pre-calculus covers logarithms and exponents, trigonometry, and algebra, and we've covered quite a large amount of ground with the videos that we've generated so far. Um, and we're really dabbling now in a very important aspect of mathematics that you really need before you can move on into calculus. And calculus isn't as bad as people think, but when we get to it, we'll discuss that. But here we go. We'll go back to the board and we'll take a look at some of the things, review some of the things that we uh, saw before. We were looking at what we call the law of sines, basically a mathematics rule that is based in really just a, just an advanced understanding of multiplication, and multiplication is just an advanced understanding of addition. So we're really building on fundamental concepts. And when you think about adding, it's just a means of counting. So counting, adding, subtracting, dividing, multiplying, these are all built upon one another and a little bit more sophisticated in each category as we move on. And this, I think, this is what they are really looking at when they look at this topic of what they call number theory. So we said that any base raised to a power p is equal to, let's say, a base raised to that um, times a base there, where p is equal to a plus b. So this is our law of exponents. Law of exponents. And here we can choose an example. We could say our base is 8. And remember, this only works with the right. So we have x. We don't know what 8 to the x is, but we're given 8 squared times 8 to the third. Well, with our law of exponents, we know that the bases are the same. And here we have a multiplication of these two bases. That means we can add these two to find x. So x is equal to 2 plus 3. And so we'll write 8 squared times 8 to the third is equal to 8 to the fifth. And basically what we have is 8 squared is 8 times 8 times 8 times 8 times 8, 8 to the third. And we're saying that is equal to 8 to the fifth. Well, what do we have here? We have 8 times 8 times 8 times 8 times 8. And how many eighths is that? That's 5/8. So our notation says we have 8 multiplied by itself 5 times. And that happens to be, well, we got 64. That's 8 squared is equal to 64. And 8 cubed is 64 times 8. That's 32. 8, 48, 51, 512. So that is equal to 512. So it's 64 times 512, and that's pretty big. So I'm going to just flip this around because I multiply better this way. 64. So we got 8, 4, 20. We got 12, 6, 7, and 30. Some of you may not be familiar with my form of multiplication. This is something that was how multiplication was taught back in the 1930s. My father taught me to multiply this way. Okay, so our value here is 32,768. That's 8 to the fifth. So let's see what we got. This is equal to 32,768. And that is our answer. I'm going to cap this so it doesn't. So let's just, I'm going to just do this on the calculator. So just to confirm it, I've got 8 raised to the fifth, and that's 32,768. So I got it correct. So this is correct. Now, that's one law of sines and an example of how we apply the law of sines. Not the law of sines, I'm sorry. The law of exponents. We're out of trigonometry. We're into exponents. But here, what if we had this n raised to the p raised to the l? Okay, the p and l could be any number. All right. What is that? Well, what we have is n to the p is n times n times n dot 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 p times n times n times n dot 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 n to the p np, I should write. That's just a notation, just saying that we've reached the pth n, okay? And we do this dot 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 to, we're gonna, let's just simplify this. We'll call n to the p, we'll call n to the p, we're gonna call it q. So we have q here times q times dot 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 q to the lth time. Okay, whatever value that q is. So that's basically what we have. And so let's take an example. Examples always work better than just general. So let's say p is 3. We're going to say n equals 5 and l equals 4. Okay? So we have n, whoops, we got 5 to the third to the fourth. And what is that? So we're going to say we got 5 times 5 times 5. And we got 5 times 5 times 5 times 5 times 5 times 5. And we got 5 times 5 times 5. And that's equal to our question mark. So here we've got one group of 5. This is 5 to the third, 5 to the third, 5 to the third, 5 to the third. And we have it 4 times. 1, 2, 3, 4. So how many 5s do we have? So we got 1, 2, 3, 4 times 3 5s. So that's equal to 5 to the 12th. So what we've seen here is n to the p raised to the l is equal to n to the p times l. It's a special case of this law. It's when we have when we're dealing with bases raised to a power raised to another power. So that's when we end up multiplying. And we can do it again if, let's say, n is 2, n is 2, p equals 5, and l equals 3. So we've got 2 to the 5th raised to the third. Yep, sorry. So according to our law, that would be 2 times 3 times 5, which is 2 to the 15th power. Well, let's see. We got 2 to the 5th, so we got that 3 times. So let's say 2 to the 5th is n equals 2 to the 5th. Well, what is 2 to the 5th? 2 to the 5th is 2 times 2 times 2 times 2 times 2, 5 times. So that's 4, 16, 32. Okay, and what do we have? That says we have n 3 times, which is n times n times n, but n is 32. So we have 32 times 32 times 32, and that's equal to, well, let's see, 32, that's 4, 6, 6, and 9. That's 4, 12, 1, 24. That's 32. That's 8, 4, 0, 2, 12, 6, 7, 0, 3. And we've got 8, 6, 7, 2, 3. So this is equal to 32,768. That's the final number. But that also is equal to 2 to the 15th. This is equal to, if we write it out fully, we've got 2 to the 5th 3 times. So we got 2, 2, 2, 2, 2, and 2, 2, 2, 2, 2, and 2, 2, 2, 2, 2 is equal to, how many 2's we got? 1, 2, 3, 4, 5. And we got 3 of them. 3 times 5 is 2 to the 15th. We got 15 2's. And if we multiply 2 to the 15th, we already calculated it, but let's just use the calculator. 2 base 2 raised to the 15th is equal to 32,768. Let's write that down. 32,768. And so there, we did it. So those were the 2 laws that we looked at, the 2 cases. So now here, let's say we've got 2, let's say we've got n to the x is equal to n to the q times n to the minus p. Well, what would that be? Well, that would be n to the q minus p. So x equals q minus p. Well, let's show it. Let's show it. This is, again, just an application of the law of exponents. So let's say we had n is 2, p is 5, and q equals minus 3. All right, so what we have here is 2 to the 5th times 2 to the minus 3 is equal, well, our rule said that should be 2 to the 5 minus 3, or 2 squared. But also, let's take a look at what this really means. We have 2 to the 5th, so that's 2 times 2 times 2 times 2 times 2. And this means 2 to the minus 3. Well, what does that mean? That means we have 2 to the minus 1 is equal to 1 over 2. So 2 to the minus 3 is equal to 1 over 2 to the 3rd. Because any number, n, to the minus p is equal to 1 over n to the p. And so if we have n to the p times n to the minus p, we end up with n to the 0, because p minus p equals 0. Well, let's take a look at that. What does that mean? Well, we didn't even finish that one yet. Let's say p is let's say n is 2, and p is 5, and q is minus 5. We have 2 times 2 times 2 times 2 times 2 times 1 over 2 times 2 times 2 times 2 times 2. Well, these just cancel out. And what do we have left? 1. So we have n to the p times n to the minus p equals n to the 0 or 1. And that's one way of showing that anything to the 0th power is equal to 1. So that's a pretty important thing. So here we had 2 to the 5th times 2 to the minus 3. So we have 1, 2 times 2 times 2. And that is equal to, well, we got 2 times 2, which is 4. So up here we had 2 to the 5th and 2 to the minus 3. 5 minus 3 is 2 squared, and that's equal to 4. So that's an important part of exponents that we need to understand when the exponent is negative. However, again, it's important that the bases be the same. Now, what if you have 16 to the 3rd times 2 to the 4th? What is that equal to? Well, we could always go 16 times 16 times 16, and that's times 2 times 2 times 2 times 2. And that is equal to, well, 16 cubed is, that's 36, 9, 16, 6, 15, 256. 256 times, that's 4 times 4 is 16, and that's equal to 256 times 16, 256 times 16, that's 36, 33, that's 12 and 15. We got 6, 5, and 2. 6, 9, 10, and 4. So that's equal to 4,096. We could do it that way, or we can try to put our bases into the same base and use the law of exponents. Well, we can't make 2 bigger. I mean, it would make it hard to find an exponent that would be, 16 to the n equals 2. that would be kind of difficult to work out right at this moment. So what we can do is we can say, well, 16 is bigger than 2. Let's try reducing 16 into some power of 2. So let's say we got 16, and we divide that by 2, and we got 8, 16, 0. Okay, so remember how we converted 2 to the 0, 2 to the 1, 2 squared, 2 to the 3rd, 2 to the 4th. So we got 0 for that one. Okay, 2 into 8, that goes 4 times. Again, that's 0, so we got a 0 there. We got 4, 2, 2, and that's 0. So we got another 0. And we've got 2 into 2 goes once. 0, 1. Okay, so in base 2, we have 1 times 2 to the 4th is equal to 16. So here we have 2 to the 4th raised to the 3rd times 2 to the 4th. And now we've got ourselves into the same base. This is what we mean by bases. Okay, so by our law of exponents, we have 3 times 4 is 12, so we have 2 to the 12th times 2 to the 4. Well, then we apply our other law of exponents, and that would be 2 to the 12th plus 4, that's 16. 2 to the 16. So let's take a look at that. 2 to the 16th. Well, we can do 16 multiplications. Let's say that would be equal to 2 to the 4 times 2 to the 4 times 2 to the 4 times 2 to the 4. That would be 8, 16. And 2 to the 4 is 2 times 2 times 2 times 2. That's 8, 16. So that's 16 times 16 times 16 times 16. So 16, that's 36. 9, 16. That's 16, 15, 2, 56. And 256, 56 times 256. Oh, that's 36, 33. That's 12, 15. Okay, 30, 25, 28, 10, 12. And we got 12. 10, 11, 4, 5. We got 6, 3, 10, 15. Okay, that's 5 and 6. So is that what we had before? 65, 536? I can't remember now. Let's see. Maybe I didn't do it right. Let's see. 2 raised to the 16. Yeah, that's 65, 536. So that answer is correct. Maybe I didn't get this. Maybe I didn't. That's correct. All right, to the 16th. So I did that math right. So this is 16 to the 3rd. So we got 16, 16. It's 36, 9, 16. That's 6, 15, 256 times 16. That's 36, 33. That's 12, 15. Then we got 6, 5, 2. We got 6, 9, 10, 4. Okay, so we got 4096 times 16, because that's 16. That's 36, 54, 57. Carry that down, 24. And we got 6, 9, 0, 4. We got 6, 13, 15, 5, 6. Yeah. So we got 65, 536. So we could have done it two ways. We could have done it by calculating, and we did in that last segment. We did it by multiplying 16 by itself 3 times, and once we got that result, we multiplied that against 2 to the fourth, which is 16, and we come out with this answer. Or we converted 16 to base 2, which was 2 to the fourth, but that was 2 to the fourth raised to the third. So that's 2 to the 12th times 2 to the fourth, which is 2 to the 16th. And then calculating that out, it gave us the same answer, 536. This is a little simpler in a way, because let's say you're on, I like the desert island analogy. When you're on a desert island and you don't have anything but sand to scribble on, like Archimedes, you ought to look up the Archimedes story. He was killed by a Roman soldier. Although the Roman leaders didn't want him dead, they recognized how exceptional Archimedes was from a physics point of view, from an engineering point of view, and from a mathematical point of view. But a common Roman soldier did not recognize who Archimedes was, and when he was contemplating, deep in contemplation, his mathematics, he was killed by the Roman soldier for not listening to him. And so there was a tragic loss there when Archimedes was killed. So, okay, so we can convert things into bases. Let's say 9 to the 6th. Oh, let's not make it so bad. Like 9 to the third times, let's say, 15 to the 2 equals, well, let's say we wanted to make this a base. And let's say, for instance, we want the base to be base 3. Base 3. How do we do that? Well, first off, we take 9 and we divide it by 3, and that we go 3 to the 0, 3 to the 1, 3 squared, 3, 3. And so our remainder here is 0 for that. 3 into 3 goes once. That's 0. So that 0 goes there, and we have a 1 there. So we have this is equal to 1 times 3 squared. So now we can rewrite this part into 3 squared to the third times 15 squared equals, we don't know yet. So now we need to get 15 into base 3. So let's use our old trick for converting into base 3. We got 3 to the 0, 3 to the 1, 3 squared, 3 to the third, 3 to the 4. Maybe we don't have to go further than that. So we go 3 times 5, it's 15 with a remainder of 0. So 0 there. 3 into 5 goes once. 3, we got a remainder of 2. So 2 goes there. And because we can't divide 3 into 1, 1 goes here. So we have, in this case, we have 3 squared times 1 we have 3 to the 1 times 2, and we have 3 to the 0 times 0. So this is 0. That would be 6, and that would be 9. And we know that adds up to 15. So, but we can't make this a nice clean base 3. This would be written 1, 2, 0, base 3. So what would we do? 120. So 3 times 4 would be 120. Now we can't do anything with that. So we're not able to get them into the same base, unfortunately. So, but if that happened to be 27, we could. But in this case, here we end up with, well, that's 3 to the 6 times 15 squared. And we could do this. We could go 3 to the 6 times 3 times 5 squared. And that would be equal to 3 to the 6 times 3 squared times 5 squared. And that would be equal to 3 to the 8th times 5 squared. So that would be a pretty big number. So let's see. This is 9 to the 3rd. So that's 9 times 9 is 81. And times 9, that's 9. That's 72. So that's 729 times 15 squared. 25, 75, 15. Okay, that's 5, 12, 225. So that's 729 times 225. That's going to be a big number. So if let's use our calculator on this occasion because it's going to be a lot of tedious mathematics and it doesn't benefit us any. So 729 times 225 equals 164,100 equals 164,025. So down here we have 3 to the 8th times 5 squared. So that would be, we would have 3, 3 to the 8th power, which is 6,000, 6,561 times 25. And that's equal to times 25, 164,025. But it didn't really benefit us any to convert this into different bases. It just gave us an exercise of how bases work, but it wasn't advantageous for us. It would have been far quicker for us just to estimate that, or not estimate, but calculate that, and then calculate that, and then multiply them together and come out with the answer. Doing this didn't really help any. But if we had a problem like this, where we have something where we can convert to base 3, so let's say 9 to the 9 squared times 27 to the third. Well, maybe we can bring those to base 3. And what would that be? Well, 9 is in base 3. We got 3, 0, 3, 1, 3 squared, 3 to the third, 3 to the fourth. So 9 is 3 into 9 goes 3, 9, 0. So we got a 0 there. 3 divided by 3 is 1, and 0 there, and 1 here. So that works out to be 3 squared. So 9 is 3 squared to the second power. Okay, now for 27. We have 27 goes 3, that's 9. 27, that's 0. So we got 0 there. 3 into 9 goes 3 times. 9, 0. So we got a 0 there. And 3 into 3 goes once. We got a 0, 0, and 1. So that's 3 to the third. So this is, we can get it into a base 3. So that's 3 to the third to the third. And because of our laws of exponents, we multiply these ones. So that's 3 to the fourth times 3 to the ninth. And then from our law of exponents, again, we got 3 to the 4 plus 9. And that's equal to 3 to the 13th power. Now, that's a big number. That's I'm choosing large numbers here. Okay, so let's just do 3 raised to the 13th power, and that's 1 million. That would have been quite a thing to calculate by hand. It's 1,594,323. So that would have been quite a task. But that's the solution to this. And let's try it. We know that 9 squared is 81. Let's try it that way. 81 times 27 times 27, that's 49, 14, 18, 14, 4, 5, that's 9, 12, 7, 29 times 27, so that's 63, 14, 20, that's 49, 51, and we got 18, 5, 14, and we add that, 0, 6, 9, 1. So it's 81 times 19,681, and that is equal to, and that's going to be a big number, 19,681 times 81, 1 million, that's equal to 1,594,161. So I did something incorrect here. Let's see. Maybe it was my multiplication over there. Let's try 27 times 27 times 27. That was correct. All right. And times 81. This is wrong. This was 323. Okay, so we matched. Our answers matched. Two different ways, two different approaches. One using the law of exponents, bringing everything into the same base, and the other was just to calculate them out. So problems like this are pretty neat because you get to see how what bases mean and what it takes to convert into a base. Now let's say we have um, we have 5 raised to 5 squared raised to the negative 5 times 5 to the 10th. And what does that equal to? Well, our law of exponents says this is 5 to the negative 10 times 5 to the 10. And that means it's 5 to the 0 or equal to 1. And how do we know that? Well, 5 squared, we have 5 squared is 5 to the minus 10. That's 5, 1 over 5 times 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's all over that. And that's times 5 times 5 times 5 times 5 times 5 times 5 times 5. 5 times 5, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9 times 5. That's 10. And we can say that multiply. And then these all cancel out. And what do we have left when all of them cancel out? We only have 1 left. 5 to the 0 is 1. So now we are dealing with negative exponents and what they mean. So let's take a look and see if there are any other things that we can do. Oh, I really am going to have to change this timer on this screensaver. Okay. Okay. So we've been looking at powers, and we've been looking at, for example, when we have the notation 10 squared, that equals 10 times 10, or we have 10 units 10 times, or 5 squared equals 5 times 5, and so on. Well, we have another operation that we call the square root, where if we have the number n, the square root of n is equal to that number multiplied by itself. That gives n. Okay, so we're looking for that number, n. So in this case, if n is equal to 25, the square root of n would be equal to the square root of 25 or equal to 5, because 5 times 5 is equal to 25. So that's basically the idea of a square root. And every number can be that has a square root. They don't always come out to be nice round numbers. For example, the square root of 100 is equal to 10, because 10 times 10 is 100. We have the same for all the squared integers. They make nice round. So if we have 7 times 7 equals, well, we could do it this way. We got 1 times 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5, 6 times 6, 7 times 7, forever. And that's equal to 1, 4, 9, 16, 25, 36, and 49, and it goes on. Well, the square roots of 1, square root of 4, square root of 9, square root of 16, square root of 25, 36, square root of 49 is equal to those numbers that gave us the square. So it's 2, 3, 4, 5, 6, and 7. And it goes on. But there are a lot of numbers in between that are squares. In fact, every number has a square root. And let's say we have 1.2 times 1.2. That's 4, 2, 2, 1. That's 1, 4, 4, 1.44. 1.44. Well, if we just saw that written, we wouldn't know necessarily that it's 1.2, that the square root of 1.44 is 1.2. I mean, we could probably guess, because we know that 12 times 12 is 144. So, I mean, it's if you use a little reasoning, you may be able to deduce some of these, but for the most part, you're not going to be able to know what the square root is. So we know that if we have a base raised to the nth power equals, let's say, 3. Well, what power does 5 have to be raised to give us 3? And that is a good question, because let's say 5 to the 1 is 5, and that's too big. 5 to the 0 is 1, and that's too small. So it's somewhere, n is somewhere between 1 and 0. Well, we can guess. Let's say that if we know that n is between n is between n is between 1 and 0. Let's try something like n equals 1/2. So 5 raised to the 1/2. Well, 5 raised to the 1/2 is, well, let's say we had 5 to the 1/2 times 5 to the 1/2. That's equal to 5 to the 1/2 plus 1/2 equals 5 to the 1 equals 5. So 5 to the 1/2 would be smaller than 5. So 5 to the 1/2 would have to be, well, we're going to just have to experiment to see what number multiplied by itself equals 5. So let's try, well, we know that 2 times 2 is 4, and we know that 3 times 3 is 9. So it's got to be between 2 and 3. And if we drew a number line, and we started at 4, 5, 6, 7, 8, 9. 5 is closer to 4 than it is to 9. So the number we're looking for is closer to 2 than it is to 3. So we're trying to reason this thing out. Well, let's try 2.1. 2.1, 1. So that's 2, 1, 2, 4. That's 4, 4, 1, 4.41. Well, that's pretty low. That's not correct. So let's try 2.2, 2.2. And we got 4, 4, 4, 4, 4, 8, 4, 4.84. Well, 4.84 is getting closer to that number 5. Let's try 2.3. 2.3. We got 9, 6, 6, 4. We overshot it. That's 12, 5.29. So it's in between 2.2 and 2.3. So we're narrowing in on it. Let's say it's 2.25. 2.25, 2.25, and we have 25, 10, 12, 10, 11, 10, 5, 4, and that is 10, 5, 4, and we add these up. We got 5, 2, 6, 9, 10. So we got 5.06, or approximately 5.1. So it's a little bit smaller than 2.25, but it's approximately there. So 5 to the 1/2 is 2.25. approximately. It's a little bigger than that. So our number n, 5 to the n equals 3, is if n equals 1/2, then 5 to the 1/2 is approximately 2.25. Approximately. I mean, it's a little smaller. Probably goes on for a long, long, long time. In fact, I think the square root of 5 is one of those numbers that has a never-ending decimal places and never repeating. I think they call those transcendental numbers. I'd have to correct myself, look it up. So 5 to the half is not what we're looking for. It's something a little bigger because 2.25 is smaller. So 5 to the n equals 3, and 1/2 is too small. So it's got to be big. It's in between 0. It's in between 1 and 1/2, because we know that 1/2 is too small. And we can continue doing this. It's a tedious problem. And basically, people have worked out tables for these things. So basically, what we've really got here at this point is if we're given a problem of this nature, 5 to the n equals 3, then we had to do guesswork. We would try 5 to the half. Well, we don't really know what 5 to the half is, so we guess. We know that the value of n's got to be between 0 and 1, because 5 to the 0 is 1, and 5 to the 1 is 5, and 3 is in between them. Well, when we estimated 5 to the half, or the square root of 5, we got approximately 2.23, which was not 3. And, it turns out that it's closer to n being 5/8. So 5 to the 5/8 is approximately 3. But how we get there is not easy. It's very complicated. And before the age of computers and calculators, people had a tough time finding those powers. But what they did in those days is they created tables. And they invented something to help them along. So what they did with a problem like this is they created what they called logarithms. So logarithm base 5 of 5 to the n is equal to the log base 5 of 3. And then we had log 5 base 5 equals log base 5 of 3. And that's 1, so n equals the log of base 5 of 3. And they would build tables using that approach. So let's take a look at creating a logarithmic table. So what we do then is take the logs of all these, and we have log base 5 of 5 to the 0, log base 5 of 5 to the 1. We have log base 5 of 5 squared, log base 5 of 5 to the 3rd, log base 5 of 5 to the 4th, log base 5 of log 5 to the 5th, and so on. We just keep going like that. We say log base 5 of 5 to the n, and that's where 5 to the n equals some big number n. Well, this is equal to log base 5 of 1. This is equal to log base 5 of 5. This is equal to log base 5 of 25. And this is equal to log base 5 of 125, and so on. This is equal to log base 5 of 625, and we'll just shorten the list a little. We got log base 5 of 5 to the n equals log n. But by definition, log base 5 to the n is equal to n times the log base 5 of 5, which is 1, so that's equal to n. So all of these then equal to, this one is 0. 0 equals, 1 equals, 2 equals, 3, and 4, so on. And then we erase that because those are all 1s. So we have 0, 1, 2, 3, 4, 5. So now we have a table that we can have n, and this is log n. So if we had somewhere between 5, let's say we wanted to calculate, 5 to the n equals 3, we see that our table here has pretty wide gaps. Here is our table heading, and if we have log of 1, that's n is 0, 5 to the 0 equals 1, 5 to the 1 equals 5, so 1 equals the log of base 5 of 5. And if we do integers, we're going to have big gaps because we're squaring, 5, 25, 5 to the third. And so every integer we go, the number gets bigger and bigger. I mean, this one, if we have 4, and log base 5 of that is 5 to the 4th is equal to 125 times 5, that's 625. 10, 12, 625, that's log of 6. So you can see how big these intervals are getting. And interpolating is going to be difficult because our numbers we have tremendous gaps between our numbers. These just keep getting bigger and bigger. I think the next one's in the thousands for n equals 5. So for a problem like this, if we were trying to find the log of 200, log of base 5 of 200, well, we know that it's going to be in between 3 and 4. But where in between 3 and 4? It's going to be the divisions have to be reduced significantly in order for us to interpolate the right number so that it yields the logarithm of 200. But people did work out these tables. It was tedious, very, very tedious. But in our case, let's give this a try. 3 is between 5 and 1, so let's erase our table here and see if we can do a linear interpretation, even though a linear interpolation isn't going to be too good. So let's put 1 there and log base 5 of 5. Okay, so we've already done 1/2 because 5 to the 1/2 is equal to 2.236. If we square that, it's approximately 5. Let's see. Just a second. I want to make sure that I'm not lying here. 5 raised to the 2.236. What am I saying? What am I doing? What? 5 y 0.5 is 2.36, not 236. Well, let's see. Yeah, 2.236, and it goes on indefinitely. So we'll leave it at that. This is an approximation. All right, so we have 1 here. Whoops. Let's draw that better. So 5 to the 1 is 5. And 5 to the half is 2.236. So 1/2 is log base 5 of 2.236. But that's still not 3. What we want is that n. that gives the value 3. So we're still between 5 and 2. 3 is in between there, and the power is in between 1/2 and 1. So let's interpolate. Let's say it's halfway between here, so 1 and 0.5, 1/2. So halfway between that would be 3/4. 3/4, because on a number line we have 0, 1, 1/2, 1/4, 3/4, 1. So we go there. 3/4 is 0.75. This is 0.5. This 0.75. And 5 raised to the 0.75 is equal to, well, let's try that by 5813. 5 raised to the 0.75, that's 3.34. We're too big, because the exact logarithm here would be 3.34. So our interpolation wasn't too good. It overshot it. So people had to be very careful when they were interpolating. In fact, actually, the power, let's say 5 raised to the 0.7 is 3.08. 5 raised to the 0.68 is too small. 5 raised to the 0.69 is almost there. 5 raised to the 0.685. Yeah, that's close enough. So it's approximately 0.684 is log base 5 of 3. Somewhere around there. Let's just confirm it one more time. I'm interpolating by guess. 5 raised to the 0.684. Yeah, that's not bad. That's not bad. That's so this is our answer. So 5 raised to the n equals 3. N equals 0.684. But again, people had worked out these tables many, many years ago. And what you do is you look up in the table for your value and what base, because the base is important. And then you were able to get what power you had to raise the base to get a particular number. So it was a long, tedious process of developing these tables of logarithms. But once they were developed, then people could use them. And they didn't have the problem that we had where the gap was so big. They calculated these logarithms accurately so that there were small gaps between, we didn't have 0 equals log base 5 of 1 and 1 equals log base 5 of 5. We didn't have that. This is a gap of 4, and so it was difficult to interpolate. They actually calculated these things exactly to a much more higher degree of resolution, and so the interpolation any interpolation that you had to do was small, and usually it was a linear interpolation, and we were doing linear interpolations. But linear interpolations aren't always a good assumption because functions, especially exponential functions, are not linear. They when you plot them, when you plot an exponential function, let's say we've got base 2, okay? Well, let's say base 3. So we have 3 to the n, and we have n. So n is 0, 1, 2, 3, 4, and we have 3 to the n. That's 3 to the 0, 3 to the 1, 3 squared, 3 to the third, 3 to the fourth. I don't think we'll be able to plot that, but that's equal to 1. This is equal to 3. This is 9. This is 27. You can see that it's starting to go up fast. So here we have 1, 2, 3. And let's say this is 10, 20, 30. All right, you got to remember that these are not even scales. And this is 1, 2, 3. And so when n is 0, we can say this is n. And this is the value of 3 to the n. Okay, so when n is 0, right there, we have 1. So that's 5, 4, 3, 2. We're somewhere around there, 1. When n is 1, this would be 5, so 3 would be about there, there. So we got that. Well, that's a pretty bad. Well, I'm sorry. That's pretty bad. So when we're at 1, we're here, there, and there. But then when we're at 2, we're at 9, which is closer to 10. So there. And when we're at 3, we're at 27 already. So that's close to 30. That's about there. So you can see that these are not linear. These make a curve. In fact, it's steeper than that because if I made an even scale of 1, 2, 3, we couldn't even plot it because it would be off the board. But you can see that it is a very steep, very curved, non-linear curve. So making linear interpolations, the only way we can make a linear interpolation valid is if we use small gaps. When we have large gaps that we had in our table, linear interpolation isn't going to work out so well. But anyway, like I said, when you go to a table of logarithms, you're not going to find that the gaps are really huge. So linear interpolation is going to be pretty darn close. So anyway, I hope this has been insightful, beneficial. I know it's a little bit difficult because the concept of logarithms is it's a function devised specifically to find the power to which a base is raised in order to get a certain number. So that's basically all a logarithm is. So anyway, this has been a long video, and we'll call it quits at this point.